Welcome to SKM and to our overview discussion today concerning reliability, availability, and PTW. Please take a moment to review this disclaimer. SKM introduced the reliability module in February 2001. Because of the variety of variables, engineering judgment is required when performing reliability calculations. In today's session, I'll be discussing distribution system reliability as an introduction, incentives to conduct a reliability study, types of interruptions, required data, reliability indices, IEEE 1493, the Gold Book Standard, network reduction modeling, software methodology, reliability library, distribution reliability example, distribution reliability cost evaluation example, final thoughts, and then resources. Power systems are vulnerable to subsystem failures for a variety of reasons. Disturbances such as lightning, switching surges also play a factor. Systems range from large utilities on grids as well as industrial, commercial, and institutional facility. Today, reliability analysis must be conducted for various reasons. To know how reliable or available your existing power system is, to design more reliable power systems, to save costs by identifying and correcting weaknesses efficiently and systematically, evaluate alternatives quickly and easily to establish an optimal design. Reliability analysis is normally implemented to assess the ability of a system to deliver uninterrupted power of a prescribed quality to loads or customer. This is normally described through reliability indices. It provides evaluation algorithms to compare different system configurations based on the importance of design criteria such as cost and reliability. The SKM reliability module is based on a paper entitled Reliability Evaluation of Power Systems by Bilton and Allen and on IEEE 493, known as the Gold Book 2007 edition. It uses the network reduction modeling method discussed in the IEEE standard. It is one of several in the reliability world. When one discusses reliability, one also needs to discuss availability. There is a multitude of incentives to analyze and improve system performance, enhance customer satisfaction, a tool for system planning and expansion, for meeting regulatory requirements, and for maintenance scheduling and resource allocation. The cause of system interruptions, aging, and or lack of maintenance, loading switching conditions, weather, vegetation, animals and pests, and human factors. The required data includes the network topology, failure information, repair times, and switching times. There are several indices within three major ones that are used. These are component reliability indices, customer-oriented indices, energy-oriented indices. Each system component can be described by a set of reliability indices or parameters. Typical reliability models are based on component failure rates and component repair time indices. Other reliability indices can be calculated from these parameters to represent the ability of a network to deliver uninterrupted power to loads or customers. The values here come from the results of the reliability analysis. The failure rate, or mean time between failure, restoration time, or mean time to repair, the mean time between failures, annual unavailability, annual availability, and reliability. Obviously, the component reliability indices are important in reliability evaluations of a system. However, they may not provide the full representation of the system behavior. Therefore, additional indices are defined for distribution systems to represent the impact of reliability on the number of loads served by a certain feeder. But in applying these indices, the zone concept needs to be understood. A zone is a portion of the power system within which a fault would cause the first upstream protective device to trip and isolate the entire zone from the system. Basically any protective device except a fuse, and the downstream system that may use the protective device as a primary protection make up a zone. A fuse is not considered the main protection device for a zone, since it cannot be switched on or off manually for isolation or rerouting power. These are the customer or at-load oriented indices. The values here come from the results of the reliability analysis. System Average Interruption Frequency Index, which is the average number of interruptions seen by each load or customer. The System Average Interruption Duration Index, which is the average duration of interruptions as seen by each load or customer. Customer Average Interruption Duration Index, which is the average time it takes to restore service to loads or customers after an interruption. Average Service Availability Index, which is the average availability of service to loads and customers. And last, the Average Service Unavailability Index, which is the average unavailability of service to the loads. These oriented indices are mathematical equation expressions, and you have to love the acronyms. Here is SAFI and SADI. KDI is the ratio of SADI and SAFI. The average service availability is the ratio of the time power is available and the time that power is expected to be provided at the load. The average service unavailability is the ratio of the time there is no power to the average expected time to have power. The energy-oriented indices represents the performance energy delivery. These are a direct measure of the lost revenue for the utility company or from lost production, and are used as reference where the company should focus to improve the service quality. There are 3 of them. 2 are here: the total energy not supplied and the average energy not supplied. And the 3rd one is the expected cost of the interruption. As stated earlier, for an industrial, this is the expected production downtime costs. IEEE 493 discusses these 5 methodologies: cost set modeling, network reduction modeling, Go algorithm modeling, Monte Carlo modeling, state space modeling. PTW uses, as stated earlier, the network reduction modeling method. In the network reduction modeling, one translates the physical network into a reliability network based on series and parallel component connections. The component-oriented indices are used. Each component is described by a probability of being available and a probability of not being available. Components are either available or not. A component is described by the annual failure rate, mean time to repair or restore, and the probability of being available, which is a computed value. When 2 components are in series, both components must be available for the connection to be available. If either of these sections fail, power to the customer downstream is interrupted. On the right side of the slide shows how the series components are drawn on one line. When two components are in parallel, only one of them needs to be available for the connection to be available. If either component is de-energized, the downstream bus remains energized. Again, the right side of the slide shows how parallel components are drawn on the one line. For PTW, as I said, network reduction method is used. The mathematical model is based on the one-line diagram, the data entry in the component editor, and data that is in the PTW library. It covers utility distribution and industrial systems. And the one line can be modeled as multiple sources with radial topology, or modeled as a single source with loops as a topology. Input can be user-defined and from a library which comes from the standard or IEEE papers, and from the electrical characteristics which are defined for nominal rating of the loads to be used for the power and energy calculations, the length of cables and transmission lines to be used for the component's total failure calculations. Ampacity capacity of components are ignored. In other words, the equipment should not be overdutied. The standard assumes this. Speaking of the PTW library, information is contained in two major areas: the customer damage function and the customer reliability data. The damage function, shown on the right, contains typical tables for outage duration times and a cost associated with that time for each typical distribution system type. The reliability data, shown in the center, contains information about the failure rate, the aging factor, and the repair time. The failure rate and repair time can be further refined by the aging history factor for each. These are tables of points, and the curves that are developed use a form-fitting polynomial expression. In the reliability data component subview of the component editor, the data for the device can be shown in two ways: user-defined, where the user manually enters failure rate, repair time, and switching time information, or by selecting the component data from the library. The source for the library information comes from both the IEEE 493 annexes and selected IEEE papers on the subject. These are the steps that are used in PTW for running a reliability study. System topology, which one creates a one-line drawing. Data entry using the component editor and library. Distribution reliability interface, which is part of the study. One selects components, does a SETI setup, performs the analysis, and then verifies and compares the indices. Again, these are the steps of running the study. We define the topology by the use of a one-line drawing. The components here are series connected such that there are 4 zones. The component editor is used to enter data. First, the general information is entered on the main subview, or page 1, the same way one enters this data for any of the PTW modules. We then go to the reliability data subview, or page, as seen on the right. The information may be entered manually or using the library for data by clicking on its button. Since we are defining a utility here, a utility device is selected from the library for its reliability data. In this slide, we are defining the transformer and a cable. As you can see, these are relatively simple when using the library. This slide, we are defining a load. The data required in the main subview is as usual, but when we go to the reliability subview, we are seeing a different form than those in the previous slide. This is because for loads we need data with cost outage time relations called customer damage functions. Again, we can enter this data manually or use the library. You will note that there are two library buttons, one for the custom damage function and one for the reliability data. Here, when we define a protective device, we use the library for the reliability data. We will get more reliability information than in earlier slides also. This additional information deals with the repair or replace data. Running a reliability study is very similar to running other PTW modules, such as transient motor starting, stability, or harmonics. They all may have multiple cases, and like in the other studies, a case can be copied, pasted, renamed as a place to start for defining that case in reliability. The right side shows several cases to be studied and compared. The center window shows us that there are two parts of a study, the reliability analysis and the cost evaluation. You can also see in this window that additional information known as indices or study setup information is required. Again, these are similar to the other studies but appear to be more complex, but they are not. This slide is showing four windows. In the upper left, we have clicked on the load point indices of the study case. Here, we select load and our bus device at the point in the system where we want study results. In the upper right, we have clicked on the protection zone indices. Again, we select protective devices that define the zones that we want result data. In both windows, the information in the database is being pulled to build the indices table that is to be used in the analysis in each specific case. In the lower left, we select components for additional consideration, whether the component is out of service or in service. If it's in service, we need to know whether the study is going to use repair or replace times. Now we select the reliability setup screen. Here we set up the study requirements for the case. In each case, we decide how we're going to treat certain devices to include, not include, handling of repair versus replace, handling of alternative power sources, and which multipliers that we want the study to use in the calculation for each case. Each case is built from the indices and from the handling setup request. So we define the load point indices, the zone indices, and the special consideration of a component, and a study set for each case. Once we have defined the study parameters and click on the Run button, we get results in a table format similar to equipment evaluation. One table is for the point locations whose values reflect nomenclature of the component reliability indices shown in an earlier slide. The other table is for the zones, and these values are expressed in nomenclature of the customer-oriented indices. We have just completed the first part of the study, the reliability. Now we will work on the second part, the cost evaluation. As you can see in the left screen, there is a utility section, which includes install cost and an evaluation, and the second distribution section with install cost and evaluation. Cost evaluation is performed based on 5 system features, each represented by a value. There are operational issues, reliability, shutdown process for maintenance or expansion, recovery capability, and costs. Weighting factors are applied to each system feature value to provide the total system evaluation value. There are 3 combinations of weighting factors, which are predefined that we can choose for each case. Reliability dominated, cost dominated are typical business. One can run the cost evaluation portion without running the reliability analysis portion, and vice versa. When one does so, there are 8 predefined distribution systems installed costs to select from. If one has modeled the system and run the reliability analysis portion, one can select the option to use the load data from the database or from that reliability study. This is recommended. There's an auto sync feature, and it is available, but making many changes or additions in the system as you build it will slow the process down, so one might wait until the end of building the system and parameter setting before selecting this feature. When highlighting the study case view, which gives us a summary view, one can easily compare different case study results for both reliability and cost evaluation. After all the work of building the system and setting the parameters for the base and possible scenarios for improvement, one may have a first response to this view, as I do. Is that all there is? Well, that's the value of PTW's reliability module. It takes a lot of work out of doing the calculations. A careful viewing will tell you that the real work now starts. As you can see, some values are improved over the base while others are not. There are trade-offs between cost and performance. Your engineering judgment and rationale now come into play as you evaluate these. As stated earlier, there are trade-offs between cost and performance. Here is the one-line drawing with reliability study result data blocks applied for the case chosen. As stated earlier, there are trade-offs between cost and performance. PTW provides you with the tool to obtain reliability, availability, and cost relationships of an existing system, or one that is being designed, or one being modified due to changes in loads or customers' expectations, as well as possible strategies to improve the delivery of uninterrupted power. The reliability module is comprehensive and, like the rest of the program, is kept up to date based on industry standards and IEEE papers on the subject, as well as additional library data and models as they become available in the industry. I urge you to take advantage of its full features. There are several sources of information that are available to you. Obviously, the IEEE standards and papers, our reliability training class 207, and on our website. I want to thank you very much for joining us today. To request a free, fully functional 30-day software demonstration CD, including reliability, contact sales@skm.com. Thank you.